Hi, and welcome to this latest video on Spectrum Analysers. We're going to be covering some basics, how to use them, how to read them, and later on I'll demonstrate some practical Spectrum Analyzer software and an actual physical device, and have a look at how they work and what they do. So when we talk about spectrum analysis, what we're really doing is trying to determine the frequency points on a graph, on a chart. So if you have, let's say, an axis of frequency, so this would be very low or zero, you could say that's probably 0 hertz, and this could be something high. Let's, for argument's sake, let's just pick a number like 100 megahertz. So here you have a line which is the x-axis, which is capable of going or displaying any frequency from very low, or let's just say that's down to 0, and up to 100 megahertz or whatever frequency you've got the device set to. This could be an audio spectrum analyzer, that could be like 20 kilohertz, or it could be 100 kilohertz, but it could be an RF type spectrum analyzer like the ones I tend to use and I'll be showing later, which go into megahertz or even gigahertz. And on this graph, on this x-axis, we can plot amplitude of whatever signal you're displaying, whatever signal you're measuring. Let's say we have a signal here, and we can say, well, if you look at it roughly, it's in the middle of the graph. It's somewhere between 0 and 100, and this would actually be displayed as a point on a spectrum analyzer of, say, 50 megahertz. So that could be 50 megahertz. That could be, these are just examples I'm picking out at random here, that could be 25 megahertz. That could be 75. Okay, so you can see we've got 3 points here, or 3 bars if you like, being displayed. That would be 0, that could be 25, 50, 75, and 100 would be here somewhere. As the frequency of the signal that we're measuring increases, we see it displayed along this x-axis. Now that's actually interesting to know straight away by looking, it allows you to display carrier signals or where a frequency of a signal generator is set to. But what you can also do is, from this, is determine the amplitude, which gives you the signal level of the peak that you happen to be looking at. And this is an important factor with spectrum analyzers, because it's important to be able to do that quite accurately as best you can. And if we took this as an example, this 50 megahertz signal that we'll happen to be measuring in our example here, we'd like to know, how high is this? Where's it actually going? And how high is it going? What's the signal level? And we do that on a calibrated scale, which is usually displayed along the left hand side, classically on a display. And these are calibrated in dBm. That's dBs relative to 1 milliwatt. So it's a dB scale, it's a logarithmic scale, and it's calibrated to dBs relative to 1 milliwatt. So they call that dBm, and that's a very standard way of displaying amplitude on spectrum analyzers using dBm. Typically you could have values in the range of, let's say, -30, -40, -50, -60, -70, that kind of range. It varies. You might be starting at -50, or you might be starting right up to 0 dBm. You can set it depending on the settings of your spectrum analyzer, but typically you could be in this sort of range, -30, -40, -50, -60, -70, something of that nature, and that would give you an amplitude reading of the carriers that you happen to be looking at. So just get my ruler. If we take this signal here, okay, and we say, okay, this point here, how high is it? And basically we're looking at -50 dBm. So that's -50 dBm of amplitude signal for this particular carrier. What about this one? Well, that looks about -60 dBm. That's smaller than that one. And what's this one? Well, if I can sort of, it's a bit messy. That's about -65. So you could say -65 dBm, -60 dBm, that's getting bigger, and -50 dBm. Now you can tell that all these values, -50, -60, and -65, are much lower than the 0 dBm reference point that we have. So we know that these powers are way below the 1 milliwatt reference for 0. 0 would be right up here somewhere. It would have to go -30, -20, -10, then 0. So you'd need a really big signal to get up there. It's off the chart. So a quick word about dBs and the logarithmic nature of the signal being displayed. Why do we use a logarithmic display in the first place? Why don't we just have it in, say, volts, where it goes like 1, 2, 3, 4, 5, 6 volts, a bit like an oscilloscope, which is a linear display in terms of amplitude? Well, we do that so we can deal with very small magnitude signals and at the same time display very large magnitude signals. We can display them all on the same screen. You can have very, very small signals down to picowatts, you know, hardly any power at all, right up to even megawatts at the top of the scale, all within the same scale, you know, because if it's displayed logarithmic, everything fits in. You can have really big magnitudes and tiny, tiny magnitudes all in the one place. You don't need a huge screen, you know, to fit all of the values in. If it was like, say, a megawatt, and you wanted to also see a signal down the bottom of like 1 microwatt, you know, imagine the amount of resolution of the screen you would need and the physical size of the screen to make it all fit. You'd need like 1 million of them or whatever it is to make them fit into the screen. You physically can't do it. And with spectrum analyzers, we usually are working with measuring very small signals, like in the receiver side of a signal. It could be just like picowatts or something. And then, you know, and on a transmitter of a radio, we could be talking about megawatts or even higher. So that's why we use the logarithmic scale. That's why we use dBs, because dBs by their very nature are logarithmic, they're not linear, and it allows you to fit everything into the same scale. Really, really useful, and that's why they do it. Now, with dBs, and dBm in particular, which is what we use for the, as I was mentioned earlier, for the spectrum analyzer scale. Just a quick, you know, an illustration of dBs and how they actually work with each other. If you had 0 dB, as I said before, 0 dBm, that is the equivalent of 1 milliwatt of energy, 1 milliwatt of power, and it's really the energy going into a 50 ohm load. And the 50 ohm load could be a dummy load, it could be an aerial system. There's a lot of things it could be, but as long as it's actually set to 50 ohm, then you know, that is the load, and that's the power being generated across that load. That determines the power. If you remember our Ohm's law video earlier, that's how it works out. The 50 ohm load is the R value. R equals 50. Now, what happens if we increase the dBm, you know, to another scale? How big does the signal get? Well, the relationship is that if you increase the level of dBm by 10, so now we say 10 dBm as an example, okay, that is the equivalent of 10 times the power. That would mean you would be generating 10 milliwatts. 20 dBm, however, is the equivalent of 100-fold, because the 10 dB was a 10-fold increase, then your 10-fold increase again for the 20 dB, so that goes up to 100 milliwatts. And so on. Every time you go up 10 dBs, you're doing a 10-fold of the last answer you had, and making it, you know, 10 times bigger again, and so it goes. And that's the logarithmic nature of dBms, and you know how you can actually, a 30 dB what would that be? That would be 100 times 10, which is like 1,000. So that would be 1,000 milliwatts, which is 1 watt. So within 3 divisions, or actually within 2 divisions, if you think about it, that would be a square. That would be a square on the screen. Or, you know, graduations here. So from 10 to 30, you've gone 10, 20, 30. So that's within 2 divisions. You've displayed a signal from 10 milliwatts, which is really small, right up to 1 watt, which is 100 times bigger. So, you know, we're really showing like a big range of signal for a small amount of actual display, if you want to call it real estate. You know, the actual part of display that you can visibly see in one go. And just a quick word on input signals going into the spectrum analyzer. You have to be very, very careful about how much signal you inject into the spectrum analyzer. And if you look at the front of the spectrum analyzer, where you've got a BNC socket or whatever connector it is, it'll always have written next to it the input limit. You know, you always have to stick to that. Don't try to put a signal in which is higher than the recommended maximum input signal on the spectrum analyzer itself. Otherwise, you will damage the analyzer. And some analyzers are very expensive, and you don't want to do that. Could cost you a lot of money to have it repaired. So always look at the BNC input and check what the maximum level is and make sure what you're putting into it doesn't exceed that. This is my rather old IFR 1200S Spectrum Analyzer with tracking generator as well built in. These things were manufactured in the 80s, probably about 1988, 1989, something like that. And at the moment I have it connected up to a transmitter which is set to 145.45 megahertz, 145.450 megahertz, which on the amateur band, that's the 2 meter band. And it's not just a spectrum analyzer, it's actually what the class as a test set. What they mean by that is it has other functionality. It's not just a spectrum analyzer, although at the moment it's configured that way, but it also has other features like modulation detection. So it'll tell you, it'll give you a measurement of deviation. It'll give you a measurement of RF power. One thing you can do with this that you cannot do with standard spectrum analyzers is you can put RF full power from the transmitter into the device to take a measurement. There's actually a big dummy load in there, a big load, a 50 ohm load, which will, in this particular model, will take up to 150 watts for a short period of time. Probably for about a minute maximum before it gets too hot. But it will comfortably take 50 to 100 watts. And as I say, that's something that you cannot do with a standard spectrum analyzer. You would fry the thing if you tried to put RF energy straight into it at that kind of level. You'd destroy it. So it is designed to take power, and that's the beauty of these test sets. It's also got other functionality, like it's got an audio tone generator calibrated at 1 kilohertz, and it has another audio generator which you can set to any frequency you like within the audio range, which is very useful for dual tone testing. It's also a receiver and a transmitter, so it's a generator as well. It will generate RF, small levels, and good enough for checking receivers, to see if the receiver's working correctly, if it's sensitive enough, or whether you actually have a problem. It's also good for calibrating S meters on radios, so you can get the S meter exactly correct to a standard. Yeah, so what else does it do? Well, it's also an oscilloscope. You can set it into an oscilloscope mode. Gives you a standard oscilloscope functionality, and it's good for up to a couple of megahertz or so. It's good for testing audio circuits and that kind of thing, testing microphones and what have you. Really good for audio. Put it back onto spectrum analyzer position. This is our span control, how many megahertz per division we're displaying, and at the moment I have it set to 1 megahertz per division, which is giving us 1, 2, 3, 4, 5, giving us about a 10 megahertz in total span, like minus 5 megahertz plus 5 megahertz, and that's the widest this goes. It gives a 10 megahertz span, but you can adjust this and tune right in and go for a much a much tighter resolution, a much smaller span, down to about 1 kilohertz per division, which is great for looking at audio frequencies within the carrier. It's also power meter, deviation. It also shows frequency error. It has an error meter. One thing I should say about this particular model as well, even though it's very old now, it has a built-in crystal oven reference. So the internal reference is actually very good, and I've had it recently calibrated as well. It's pretty much spot on. So everything's reading correct. We'll have a digital display which gives us various readouts for frequency, power, frequency error, that kind of thing. All in all, it's a fantastic all-around unit for testing pretty much everything you need to test with radio equipment. It's specifically designed for aircraft radio, amateur radio, mobile radio, anything like that. It's designed to check the RF output, the modulation levels, frequency error, whether it's calibrated or not, and the other way, turning it into a generator, sending the signal the other way into the receiver side and checking out the receiver performance. It also does some clever stuff, like it does sinad measurements as well, which you can put an audio into that from the output of the radio into that, and you can actually determine the noise level of the receiver as well, and whether it's working to its optimum settings. Very good for setting up front ends and that kind of thing, and IF strips. So yeah, here's a practical application for the IFR 1200S, and like I say, this is actually quite an old machine now. These days you can get, obviously brand new machines which have a digital display, but pretty much have the same functionality. Right, so as I said, I've got the radio set here, set to 145.450. We can demonstrate some signals. So if I just key up, what we call key up, in other words transmit, you will see an output on display, and there it is. I'm going to increase the span to zoom in effect, and you can see a very clear signal on the display there. And if I talk through here, you'll actually hear me speak.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
So it's actually working like a receiver as well. So every time you transmit, you press the little button here. The radio is now transmitting into the IFR, and we're seeing the signal here. If we look at the readout of the display, it is actually 145.450. It's pretty much spot on, and the frequency error is negligible. There's a little bit of error, but it's not much. The output power is showing at, put this on the digital display, 5 watts from the radio, and the digital display confirms that it's 4.97 watts. 4.97. So it's given us a really accurate power reading right there as well. Here's another much more modern type of spectrum analyzer board, and what this is a unit which you plug into your PC through a USB socket. It has an input, RF input, and it has an RF output, because this is also a tracking generator and a spectrum analyzer in one unit. And these are incredibly cheap on eBay at the moment, you know, about 30 or 40 pounds, something like that. Really cheap, and you can get them all your favorite Chinese outlets like Banggood and places like that, and AliExpress. They're obviously, you know, they're built at a price, and the quality reflects that. They're not perfect, but for what they are, it's a great way of getting started into using spectrum analyzers. It's a very cheap way of getting into experimenting with spectrum analyzers, and even a tracking generator output. Like I say, the quality's not brilliant, but certainly gives you an indication which can be useful if you're testing circuits. You couldn't plug anything like this directly into a radio. It would just blow it up straight away, because you'd have too much power coming in. So you'd have to use it with a direct coupler and a dummy load, something of that nature, to sample the RF safely before you inject it into the spectrum analyzer input here through the connector there. So this particular one goes from 35 megahertz minimum span, like your left point of your screen if you like, 35 megahertz. So it starts at 35 megahertz, it won't see anything lower than that, but it goes up to 4.4 gigahertz, 4,400 megahertz. So it's very high into the microwave band. So it's particularly good for VHF, UHF, and up over readings, and it also outputs at those frequencies as well. So it'll put out a 0 dBm calibrated output signal, and it's reasonably accurate across the band. I think it's quoted as being within 2 dB or something of that nature, right across the band. So it's not bad at all. Maybe it's even better than that, possibly down to 1 dB. That's a really simple, cheap board with surface mount components on it, and you can get them in boxes as well. You get them in metal cases. I didn't bother with that. I just got the board as cheaply as possible, because I just wanted to see how it would work first. Now that I've tried it, yeah, it's not too bad. Yeah, it's good for, you know, rough indications of things, but it does have limits, and you can't always trust what you see on the screen. It works with a PC, and it comes with some software. You put the software in your computer, plug this in, and away you go. So great cheap way of getting started if you need a cheap spectrum analyzer just to learn how they work and have a bit play in the lab. Okay, so here's an actual practical example of using a spectrum analyzer. What we're doing here is we have a homemade frequency source or signal generator device. Runs on 12 volts, and it's being supplied from the power supply. All this is really a high frequency oscillator. It's actually written on the case here what the frequency is, and it's 1268 megahertz, which is 1.268 gigahertz. And it's also written on here, because it's already been calibrated, minus 10 dBm. So that's the output level signal we expect from the output here into a 50 ohm load, minus 10 dBm. And minus 10 dBm, that's the equivalent to 100 microwatts. They're the same. So it's just another way of saying 100 microwatts basically. So we've got 100 microwatts of power, of energy, being generated from this device. And this comes through a series of RF connectors. These are just adapters, there's no attenuation or anything. That's coming straight into this device here. Now this is the spectrum analyzer interface itself. In this particular case I'm using a unit called an SDR Play, which is also used as a radio receiver, and a lot of radio hams use these. It has a very wide bandwidth in terms of for the frequencies that it can detect. Goes very low and goes very high, and at the moment I'm using it as the spectrum analyzer interface, because it's also a calibrated device. They're very accurate to use them as spectrum analyzers, and they don't cost that much money in terms of how much an actual dedicated spectrum analyzer costs. This is just a fraction of the price, and they're very good. So if you're wanting to get into doing some spectrum analysis and you need something which is actually calibrated in terms of amplitude and frequency, these are actually a very cost-effective way of doing it. So just to recap, we've got the signal generator here, generator signal 1268 megahertz, or 1.268 megahertz through some adapters, no attenuation, it's just a straight through signal, into the Spectrum Analyzer interface. This comes through a USB connector and that goes to the PC. So let's go and have a look at the PC, power this on, and we'll see what the signal actually looks like. Okay, so this is the PC screen, the output from the Spectrum Analyzer interface. Here we see a very large peak right in the middle there, and the frequency is displayed as 1267.9673 megahertz, which is 1.267 gigahertz, which is pretty much exactly what we had written on the calibrated source. And the actual, so that's telling us the frequency here. The output amplitude, this is minus 10 dBm, minus 20 dBm, minus 30 dBm, like we were talking about earlier. And we can use our cursor here, bring it across to the point, and the amplitude says minus, I'm making it about minus 11.6 dBm. So it's slightly lower than what we had written on the box, but it's pretty close. It's within a dB and a dB and a half. It's not too far out. So it's minus 11.6 dBm, and the frequency is reading as 1267.967 megahertz, or 1.267 gigahertz. So this display is actually showing us amplitude, and it's showing us the frequency on the x-axis. With software like this, with more modern spectrum analyzers, you've got the ability to do things like freeze frame, a bit like a storage scope, where you can actually freeze the whole thing and then you can go in and you can do some analysis, and it's not changing all of the time. We'll release that, and there you go. And you've also got like memories and traces and lots of mathematical functions as well. You can compare two signals, for example, and you can see what the dB, the relative difference between the 2 points is in terms of amplitude. You can do mathematics like that. Or if you've got multiple peaks, you can have them automatically identified by amplitude and frequency markers. So there's a lot of things you can do. You can also zoom in, you can reduce the span. At the moment I've got it set to 100 kilohertz per each of these divisions. So each one of these is 100 kilohertz, then another 100, then another 100, another 100, and so on. So we can go smaller, let's say 20 kilohertz. Now it's 20 kilohertz per division. It's still a very narrow peak, so we'll go further in. Let's try 10. And now you can see that we're moving away from the center line because our frequency is not as accurate as it could be. So I'm just going to adjust the frequency slightly here, and you'll see this drift into the center. There you are. Now we've got a more accurate frequency display here, keeping it in the center. That's 10 kilohertz per division. Let's go tighter again. Now it's 5 kilohertz, and you can see this is starting to open out. 2 kilohertz, and at this point we can see the actual peak here, and we can tell that it's actually being very, very narrow. It's not a modulated carrier, it's just a constant carrier, so there's no modulation here. It's just a straight carrier, and that's 1 kilohertz, which is the narrowest that this particular spectrum analyzer display goes. So this actually goes 1 kilohertz for every division, for every block here. And you can see the actual carrier there, but it's getting rather digitized. You can see all these little squares and stuff. It's right down to the edge of the capabilities of the analyzer unit. So we'll put that back on 100 kilohertz per division there. So yeah, that's a more modern type of spectrum analyzer. This is using an SDR Play device, which is the block I've just showed you earlier there. Okay, so hope you've enjoyed the video today on spectrum analyzers and how to use them. And we covered a few aspects. We haven't covered everything that spectrum analyzers can actually do. We haven't really looked at much at harmonic content of transmitter circuits, that kind of thing, and looked at the different levels of harmonics, the second, the third, the fourth, and so on, harmonic of the fundamental frequencies. We haven't really gone into that. There's a good few things we haven't really covered, but it is the basic principles of spectrum analyzers, and I just wanted to basically, give you a feel if you haven't used one before. I hope that was helpful in some way and you've taken something away from it. So thanks very much for watching, and to the next time.